Alright, so in this video we're going to do a little bit of product design, and we're going to design an electric storage heater. And what we're going to think about is choosing a good material to use as a storage heater. So first thing, if you don't know what a storage heater is, I highly suggest you pause this video now and do a little bit of Googling and find out exactly what one is and how it works, because they're quite interesting devices and a lot of places have them as a method of heating. So storage heaters essentially are a large amount of a material, and we use them as a way of storing thermal energy by raising their temperature. So what we're going to do in this video is we're going to compare two possible materials we could use for a storage heater and use the learning about specific heat capacity to understand why one material is better than the other. So my first question, we've got some basic properties of concrete and water. So we've got their density, we've got their specific heat capacity, and we've got the point at which they will change state when we raise their temperature. So water is going to boil and turn into water vapor, concrete might melt and turn into liquid concrete. So what we need to do first of all is, if we have 1 kilogram of both substances, which material could we use to store more thermal energy if it starts as room temperature? So pause this video now, see if you can figure it out, and then we'll talk about how I explain what happens. Okay, so now you've had a chance to have a crack on your own. Let's go through the stages I went through. So first off, if we compare the two specific heat capacities, so water has a higher specific heat capacity than concrete, which means it takes more energy to increase the temperature of water by 1 degree than it does for concrete, which is good if you're wanting it as a storage mechanism, because for each degree we increase this temperature, it's stored more energy. And specifically in this case, it stores 3.5 times much as energy for each degree of temperature rise that we have. So water, in terms of specific heat capacity, water is better. Let's now have a look at the possible temperature rise we can get. So before we start boiling water and have it turn into a gas, which would cause us quite a big problem if we're trying to store thermal energy, because it would start expanding and pressurizing inside the heater, we can only take water up to a maximum of 100 degrees before that becomes a problem. With concrete, we could take it up to a maximum of 2,500 degrees. So we can essentially increase the temperature of concrete 31 times more than we can for water. So if we put those two things together, so what we're going to end up doing is dividing 31 by 3.5, we get that concrete per kilogram can store about 9 times more energy than water can. So these rough back of the envelope style calculations we've done, we reckon concrete per kilogram is better than water. Okay, so we're going to dig into this one a little bit deeper, because hopefully, as some of you are thinking right now, surely we're not going to have a heater at 2,500 degrees. Good question. Absolutely, we're not. So what we're going to do is now start getting into some actual practical thinking about this scenario. So first off, let's think about the size of heater we are using so we can get an idea of how much material. So we did it per kilogram before. How much material could we actually reasonably have in a storage heater? So I have one in my room here. So I took out a ruler and measured it, and we've got these dimensions to the nearest centimeter. So the first thing we're going to do is work out what its volume is in meter cubed, so then we can think about calculating the mass. So that's what I'd like you to have a go at now. I'd like to calculate the volume in meters cubed, and then we're going to calculate the mass of concrete in water, and you might need to flip back to the starting slide to pick up the values for density that we have earlier. Okay, so now you've had a chance to pause the video. Let's have a look at each of these in turn. So there's two ways of doing this volume calculation. One method, you can convert all of the lengths into meters straight away and then multiply them together to give you the volume in meters cubed. That's one method for doing it. And we are assuming it's a cuboid style shape, so we get the volume by just multiplying all the lengths together. The other way we can do it is we can calculate the volume in centimeters cubed by just multiplying all the lengths in centimeters. And then by knowing that 1 meter cubed is 1,000,000 centimeters cubed, we can calculate the volume and get the same value. So either way we do it's fine. My preference is the one on the left because it's more straightforward to calculate. Then, now we've got the volume, we can use the densities to figure out what the masses are. So let's do it for water first of all. So we should know that density is the mass per unit volume, which means mass is density times volume once we rearrange that. So the density of water is 1,000 kilograms per meter cubed. So this is why we needed the volume in meters cubed, which gives us 40 kilograms of water inside this volume. We can do the same thing for concrete, which is why I've used CC as like the little subscript there. So from the first slide, we have the density of concrete is 4,200 kilograms per meter cubed, times it by the number of meters cubed, gives us the mass of concrete we can have is 168. So actually, inside a storage heater of the same size, we can have a much larger mass of concrete, which is going to give us a larger amount of energy stored. So in terms of the mass of concrete that we can see that concrete, we can have about 4 times as much as water. So that's going to be our preferred material in terms of the mass. Okay, so now let's have a think about the practicality of this. So the next question to think about would be, would the volume of concrete or of water, depending on which we use, be actually larger or smaller than the volume that we calculated? And to explain your reasoning. So again, pause the video now, have a go at explaining your answer to this question. I highly recommend you write it down to actually put it into words what you think, and then I'll explain to you how I thought about it. Okay, so if we have a look. Okay, so we use the dimensions of the heater to get the volume, but in reality, we're going to need other parts inside our material. So for a start, we're going to need some sort of electrical heater inside there so we can actually warm up the material. So all these other parts are going to reduce the volume available to have as the storage material, either our water or concrete. So that would be an like the maximum volume we can have. It's most likely to be less than that value. Okay, so then let's think about the maximum temperature change and therefore the maximum amount of heat energy that we could store. So first of all, let's have a look at those two. So we saw this one earlier during the calculation. So first off, our maximum temperature water can go up to 100 before it changes state. The maximum that concrete could go up to was 2,500, and therefore we can work out what the maximum temperature change is. So therefore, what I'd like you to do is, now we've worked out the masses of the material in the previous part of the question, I'd like you to figure out what the new maximum quantity of energy that we could store in each material. So pause it and have a go at that now. Okay, so let's have a look at this one. So we're going to use Q equals mc delta T to work this out. So we saw from the last question we can get 40 kilograms of water. We know the specific heat capacity of water, and we know the maximum temperature change, and that gives us an energy. And we can do the same process for concrete. So what you can see is we can store with these two masses and these two temperature changes, we can store 10 times as much energy in concrete as we can in water. So concrete's looking pretty good at this stage. But now what we're going to think about is giving this a bit more reality, because we're not going to go up to 2,500 in a real storage heater. So let's start thinking about that. So storage heaters typically would only go up to about 50 degrees Celsius. So what I need to do is pause the video now and have a think to yourself, why might we only go up to 50 degrees? What reason have we got for that? Okay, so now you had a chance to think and put down some ideas. Here's my explanation for this. So the first thing is human skin starts to burn at about 60 degrees. So that's why things feel hot when you touch them. It means they're above 60 degrees. And we've learned that that's doing damage and our reflexes move our hand away. So by keeping the heater at 50 degrees, it reduces the risk of burns to people around. So this is probably the main reason that we don't go above 50 degrees. It's a safety thing. Okay, so let's take that into account with our calculations now. So if instead we go to a 55 degrees centigrade, so still below the 60, what I'd like you to do now is we know the two masses of concrete and water, and now we've got a new final temperature for each of them. Calculate the new quantity of energy stored in each material. So pause the video and have a crack at that now. Okay, so let's have a look now you've had a chance to work this out. So first off, we're going to use Q equals mc delta T. So mass of water was 40 kilograms, mass of concrete was 168. We know the specific heats in joules per kilogram, but now they both started at 20 degrees room temperature, so each of them would have a temperature change of 35 degrees. And we can see that when we implement that water and concrete are much closer together, but that concrete still can store slightly more energy because of the much larger mass that we've got. So for the same temperature change, concrete is still a better storage medium than water is, but not nearly as good as it was before. Okay, so what we do now is think about why things feel a different temperature. So if you touch the concrete at 55 degrees, and if you touch the water at 55 degrees, you would feel that one of them was hotter than the other. So in this example, I've said it feels like the concrete is hotter than the water, even though we know they're both at 55 degrees. So what I'd like to do is have a go at explaining why this is the case, even though they're the same temperature. So have a go, and then we'll review what I've got down for this as well. Okay, so let's have a look. So this is all down to thermal conductivity. Okay, so concrete is a better conductor than water is. What that means is it can transfer more thermal energy per second. That's what we really mean by that. And that's what we feel when we feel temperature. So when something feels hot, it means it's transferring thermal energy to us at a very high rate. And when something feels cold, it's transferring thermal energy away from us at a high rate. That's how our bodies measure temperature. We actually don't have a way of measuring the temperature in like degrees or anything like that. We just measure the rate at which thermal energy is either transferred to us or away from us. And if you'd like to know a little bit more about that, I'd highly recommend this video that from Veritasium, which is an excellent YouTube channel, called Misconceptions about Temperature, because it goes into that whole process in more detail and poses you some problems to have a look at. So do check that out. Okay, so let's go back to our a scenario. So using the answer to the previous question, explain why we would want a concrete storage heater rather than a water room to heat a cold room in the morning. So we're just thinking about our answer to the last question. We're not thinking about the amount of thermal energy stored here. So again, have a think, write down what you reckon, and then we'll review what I've got for this. Okay, so let's take a look. So we saw from previously that concrete has a higher thermal conductivity than water, at least in that example. And what that means is the concrete heater will transfer thermal energy to the air in the room at a higher rate, or it will transfer more energy per second, is what that means. And therefore what that means is that the temperature of the room will reach the level that we're looking for in a shorter period of time if we transfer thermal energy at a higher rate. So that's what we're looking for, and that's why we would want concrete rather than water in terms of thermal conductivity. So let's go back to the question I posed to the students in class. So at GCSE, we do have concrete storage heaters. So the question is, should we replace them with water storage heaters, and to explain the reasons why that would be the case. So again, pause the video, try and think of all of the possible reasons that we may or may not want to switch them, and then we'll have a look at the reasons that I've got here. Okay, so let's have a look at my reasons. So I picked two key things in terms of explaining this. One, our concrete can store more energy for the same volume of material than water, which we already saw earlier, and it can also transfer it to the room at a higher rate. And those are the two reasons why I think we should pick concrete heaters rather than water. So on the flip side of that, what I haven't put here is we might thinking, well, concrete might be more expensive than water. Fair point. That could be a reason we pick water instead. And we can come up with a few different reasons, but I think these are the two key ones that we'd be looking for, but that maybe you could start thinking water might be cheaper and therefore we should use that one instead. Okay, so that finishes this video looking at thermal storage heaters. I hope that you found that useful to see some of the application of your thermal energy knowledge. At this point, what I do is pause this video and go back through all of the calculations and explanations you've done and make sure you can explain the stages of the calculations you've done and that you fully understand the explanations for the questions we've done as well. And if you can't, go back and review those now. But if you're happy with all of those, that means we're at an end with this video. And I'd just like to thank you very much for taking the time to watch. And if you have any questions, please feel free to comment and let me know, and I'll try and get back to you as soon as I can.